In Chapter 15, Section 3, we're going to look at double integrals with polar coordinates. So we'll find that this will simplify and make some problems a lot simpler, which is a good thing. So if we look at problem 1, it says a region R is shown. Decide whether to use polar coordinates or rectangular coordinates and write the region as a function of x and y, dA as an iterated integral, where f is an arbitrary continuous function on R. Now, with triangles or rectangular shapes, it makes sense just to use rectangular coordinates. So we're going to really like polar coordinates when we have curves, circles, things like that. So this one we're going to keep in Cartesian coordinates, rectangular coordinates, and so we just have to figure out the limits of integration. So one of the main things is we have to find the equation for this line. So this line is going to be some mx plus b. And so we just need slope formula to figure this out. So we have a point at minus 1, 0, and we have a point at 1, 1. And so the slope of this line is going to be y2, which is 1, minus y1, which is 0, divided by x2, which is 1, minus x1, which is negative 1. So we're going to get this as 1 over 2, so the slope is positive 1/2. And then we just need to plug in one of those points into point slope form. And let's go with the one where y is 0, the first point. So this is 1/2 x minus 1. Y is equal to 1/2 x plus 1/2, and they're going to write that as x plus 1 over 2. So that is the equation of that line, and that is going to be how y varies. So we're going to have y varying from 0 to this line, and we're going to have x varying from minus 1 to 1. So the integral is going to be this function, which we don't know what it is, the overarching function that's going to give us a volume above this shape. And we're going to have, it actually doesn't matter, dx, dy. I think the answer, they have dy dx. So they are doing vertical rectangles, and they have dx there, so that would be the last term. And the y, I already said, varies from 0 to the equation of this line, y equals x plus 1 over 2, and x goes from minus 1 to 1. And if you look, that would be the proper setup for problem 1. Okay, problem 2 is where we are going to start using the polar coordinates. So let's get some review equations down. So we know that r squared, actually let me write left to right, rectangular to polar, x squared plus y squared equals radius squared. We know x equals r cosine theta, and we know y equals r sine theta. And the integral becomes, in polar coordinates, we have some alpha, beta, and we have some h1 as a function of alpha, theta, h2 as a function of theta, and it's going to be the function. Instead of x, we put r cosine theta, and instead of y, we put r sine theta, and we have r dr d theta. Now let's see what this was in the previous form. So in the previous form, it was a function of x, y, and it would just be dx, dy, for example. And in that case, we would have some x1, x2, y1, y2. So you can see there's a one-to-one mapping of x and r cosine theta and y and r sine theta. The only thing that's kind of interesting that changes is dA, which is this term, is now r dr d theta. So we pick up an extra r in the form of the polar double integral. So we have to remember to add this r here. That is one small difference between rectangular coordinates and polar coordinates in these double integrals. Okay, so in problem 2 it says evaluate the given integral by changing to polar coordinates. We have the double integral of sine of x squared plus y squared dA. And then it says where r is the region in the first quadrant between the circles with center, the origin, and radii 3 and 5. So the region is in the first quadrant, and there's two circles centered at the origin, and one has radius 3 and one has radius 5. So 3, 5. So we have a circle like this, and we have a circle like this. 3, 5, 3, 5. And the actual region is right here. So this is R. Okay, so we have to change this to polar coordinates. So we're going to first change this to sine. The first thing we're going to replace this with is we can write x squared plus y squared as radius squared. So we're going to write that as radius squared. dA from here we're going to write as r dr d theta. Now, based on this drawing over here, I can see that r varies between 3 and 5. Okay, so these are really r values, distance from the center. And then theta is measured from the x-axis and goes counterclockwise. So this would be theta, and if you look, theta is bound by 0, the x-axis, and pi over 2, which is the y-axis. So there's only 90 degrees worth of this region here. So plugging that in, r is the first variable written dr, so we're going to write our limits for that first, 3 and 5. Theta is second, so we're going to write that next, 0 to pi over 2. Okay, and that's it. So that is the correct setup. Once we have that, that's really the hard part is done. So now we're going to perform this antiderivative. So the first thing we're going to do is we're going to set u equal to r squared. Therefore, du is 2r dr. Or solving for dr, we would have dr is du over 2r. And we're going to plug that into the double integral. 0 pi over 2, 3 to 5, sine of u squared times r times dr, which is du over 2r. And again, whenever we use a u substitution, this should happen. All the r terms cancel. And we have 1/2 here, which I'm going to pull all the way out front. 0 to pi over 2. Let's actually change the limits of integration. I don't do this often, but let's try it. So if u is r squared, we're going to plug in the first limit, the lower limit, which is 3. So we're going to say u of 3 would be 3 squared, or 9. So now this bottom limit is 9. Then we're going to plug in the old upper limit of 5, u of 5, which would be 5 squared, which is 25. So this upper limit is 25. Now the nice thing about doing that is I do not have to back substitute in for u at the end. We can just calculate the antiderivative of u and plug in these numbers. Okay, so the derivative was sine u du. And the antiderivative of sine is negative cosine. So we're going to get, this is negative cosine of u from 9 to 25, and then we have d theta. So we're going to get 1/2 antiderivative 0 to pi over 2 of negative cosine of 25 minus negative cosine of 9, and that's going to give us 1/2 antiderivative 0 to pi over 2 of negative cosine 25 plus cosine of 9 d theta. Okay, now none of those terms have a theta in them, so the antiderivative of all that, they're basically just constants now. So the antiderivative of this would just be adding a theta to both terms and then evaluating it from the lower limit to the upper limit. Kind of run out of room here. Let's go up to the top and continue this. So we have, this is going to be, actually let me do green so you can see. So we take this and we go to the top, and we're going to say this is 1/2. The antiderivative would be theta times minus cosine 25 plus cosine 9. And that theta is going from 0 to pi over 2. So we're going to have 1/2 pi over 2 times minus cosine 25 plus cosine 9. And the 0 we don't have to plug in because it won't add anything to this. So the final answer is pi over 4. And it looks like I swapped the order here. Have the positive term first, that's common. Then the minus term, cosine 25. So that will be the final result for that one. And you might argue, didn't seem like we saved a lot of work. Well, if you try this problem in rectangular coordinates, I can just tell you it is a lot of work. It's a lot more work than what we did here. Okay, problem 3. Okay, it says use a double integral to find the area of the region enclosed by the curve r equals 6 plus 2 cosine theta. Okay, so we have r equals 6 plus 2 cosine theta, and let me show you what that looks like with Desmos so we can get a sense of the drawing for this. Okay, so this is what the graph looks like in Desmos. This is called a cardioid because it looks like a heart. And so we're going to, when we get to the other side, we're going to have our limits go from r is 0, so r dr d theta. So r is going to start here, that's r0. And it's going to go from this point, which this is governed by this equation, r equals 6 plus 2 cosine theta. So that's going to be the upper limit of r. And then our theta is going to go from 0 to 2 pi. So basically we're going to grab all these radii, an infinite number of them, from 0 to 2 pi of this cardioid, all the way back to 2 pi. So that's the idea. So let's head back and see how to do it. Okay, so I had started it. We said theta should go from 0 to 2 pi. Radius goes from 0 to the equation 6 plus 2 cosine theta. And there is no other function, so it's just going to be r dr d theta, which is again dA. So when we had no function in the rectangular coordinates, it was just dx dy. In polar, with no function, you write r dr d theta. Okay, so the first thing we're integrating with is r, so this is going to be 0 to 2 pi. The antiderivative of r is r squared over 2, evaluated from 0 to 6 plus 2 cosine theta, and then it's d theta. So that's going to give us 1/2, I'll pull out, 0 to 2 pi, and then it's the quantity 6 plus 2 cosine theta squared, and then d theta. And the 0 on the lower limit will not matter because 0 squared is 0. So that's what we end up with. Now we have to FOIL that. So we're going to get 36 plus 12 cosine theta plus 12 cosine theta is 24 cosine theta plus 4 cosine squared theta, d theta. Okay, now all of these are pretty easy to integrate. In fact, let's do some of them. We're going to get 1/2 times 36 theta from 0 to 2 pi. So I'm going to do each of these terms as its own integral. Then we're going to get plus 1/2 times 24. The antiderivative of cosine is sine theta from 0 to 2 pi. The hard one is 4 cosine squared theta. So the antiderivative of cosine squared is not so easily done. In fact, we're going to do a change of form. So trig tells us, recall, that cosine squared theta can be changed into 1 plus cosine 2 theta over 2. So we're going to take the antiderivative of that. So it's going to be plus 1/2 from the outside of this integral times the 4 times the 1/2 from this formula of 1, which is going to become theta, plus it's going to be the same stuff, 1/2 4, another 1/2, and then the antiderivative of cosine 2 theta is going to be, oh boy, I'm going to run out of room here. It's going to be sine 2 theta over 2. Okay, a lot going on there. So let's see if we can start to simplify this. This is going to be 18 theta from 0 to 2 pi. This is going to be plus 12 sine theta from 0 to 2 pi. This is going to be plus 2 times 1/2, which is 1/2 of 4 is 2, times 1/2 is 1, so you just get theta from 0 to 2 pi. Then we get, same idea, 1/2 of 4 is 2, 1/2 of 2 is 1, 1/2 of 1 is 1/2 sine of 2 theta from 0 to 2 pi. So we're going to get 18 times 2 pi. Notice these zeros are all going to go away, so I don't need the lower limit at all. Plus 12 sine of 2 pi plus 2 pi plus 1/2 sine of 4 pi. Okay, and sine of 2 pi is 0, so that whole term goes away. Sine of 4 pi is 0, so that whole term goes away. So the only thing we're left with is 18 times 2 pi, which is 36 pi, plus this 2 pi, so the whole thing is just 38 pi. Okay, so that's how you would handle that particular trig polar problem. Problem 4. Sketch the region whose area is given by the integral and evaluate the integrals. So we have the integral from pi to 2 pi and 4 to 7 of 4r dr d theta. Okay, this is problem 4. So just based on the r limits, these are circles. So if r is 4, it's a circle of 4. If r is 7, it's a circle of 7. So I've got to put a 4 here, and a 7, 4, 7, these are negatives, and then 4, 7, minus 4, minus 7. So these two regions are going to look like this. I've got a circle 4. We've got a circle through 7, like this. Now, theta goes from pi to 2 pi. So theta is going to start over here at pi and go to 2 pi. So the region is only this bottom half. So the region is the in between these two circles in the lower hemisphere of the particular grid or map. Okay, so that's sketching it. Now let's perform this antiderivative. So we would have, let's just pull 4 out of the whole thing. 2 pi. Antiderivative of r would be r squared over 2. And that's going to now be evaluated from 4 to 7. And that's d theta. So let's pull out the 1/2 also. So this is 4 times 1/2. And we're going to get pi to 2 pi. And now it's going to be 7 squared minus 4 squared. D theta. This is 4 times 1/2 is 2. Pi to 2 pi. And we're going to get 49 minus 16. D theta. And that's going to equal 32 times the antiderivative of pi, 2 pi, 33 d theta. But we can pull that out and call it 2 times 33, which is 66, pi to 2 pi of just d theta. That's going to be 66. Antiderivative of d theta is just theta from pi to 2 pi. So we get 66 times 2 pi minus pi. This is 66 times pi. Okay, so good to draw it. It's helpful to draw it to see what are we actually calculating, the where's the actual region, and then we can kind of better understand how they got the limits of integration. Problem 5. Use polar coordinates to find the volume of the given solid under the cone z equals square root of x squared plus y squared, and above the disk x squared plus y squared less than equal to 16. Okay, so let's work with this first. So z is equal to the square root of x squared plus y squared. Well, one of the first things I wrote was x squared plus y squared equals r squared. So in polar coordinates, this would be the square root of r squared, which is r. Then they say above the disk, so that's going to be the region we draw. This is x squared plus y squared is less than or equal to 16. Well, this is really saying x squared plus y squared is less than or equal to 4 squared. And this is going to be r squared has to be less than or equal to 4 squared, or r is less than or equal to 4. So when we draw this region that they're interested in finding, it's going to be 4, 4, 4, 4. And it's another circle. So they're looking for this whole thing. That circle radius less than or equal to 4. So we set up our antiderivative. It would be, notice that theta is going to go the entire, it's going to start at x and go the entire way around. So that's going to be 0 to 2 pi. Radius is going to go from 0 to 4. The equation we're doing is z, but that's r, so we're going to plug in r. Then we have dA, which is r dr d theta. So notice that this r went right there. So that's the actual function we are calculating. And this is going to be equal to the antiderivative of 0 to 2 pi, antiderivative of 0, 4 of r squared dr d theta. Well, that antiderivative would be r cubed over 3, and that's going from 0 to 4. d theta, this would be 0 to 2 pi. 4 to the third over 3 would be 64 over 3. Not 64, 48. This would be 48 over 3. And then that is 0 won't count, so we don't need to plug in the lower limit, and that's d theta. Okay, so then we'll factor out that 64 over 3, and we'll go from 0 to 2 pi of d theta. This looks very similar to the one we just did. 64 over 3, the antiderivative of d theta is theta, and that's going from 0 to 2 pi. So we're going to get 64 over 3 times the quantity, 2 pi minus 0, and that's going to equal 128 pi over 3. That would be the volume under that cone and above the disk r less than 4. Problem 6. Use polar coordinates to find the volume of the given solid below the paraboloid, z equal a bunch of stuff, and above the xy plane. So for the first thing, just like last time, we're going to isolate z, and they actually did it for us, so that's nice. Z is equal to 8 minus 2x squared minus 2y squared, and above the xy plane. So this is going to be 8. Factor out a minus 2, which is going to give us x squared plus y squared, or z is equal to 8 minus 2r squared. So x squared plus y squared we can write as r squared, so now z is in polar coordinates. Okay, then we are going to look at if it says above the xy plane, above the xy plane. So notice that at the xy plane, z is 0. So we have at xy plane, z equal to 0. So we're actually going to plug that in and solve for r. So we're going to say let z be 0 from this polar equation, and then let's solve for r. So we just do our algebra there, and we'll get r has to be equal to 2 at the most. And I don't need plus or minus here because we know if r was a negative, then we could be below the xy plane. So let's keep it as just positive. And so we're going to have our limits of integration are 0 to r to 2. And since they don't tell us about theta, we're going to say that theta must go from 0 to 2 pi. So our antiderivative becomes 0 to 2 pi, 0 to 2, of the z equation, which is 8 minus 2r squared, times r dr d theta. Okay, now we'll distribute that r. We'll get 0 to 2 pi, 0 to 2. We'll get 8r minus 2r cubed dr d theta. And that's going to equal 0 to 2 pi. This is going to be 8r squared over 2 minus 2r4 over 4 from 0 to 2 d theta. This is 0 to 2 pi. This is really 4 times r squared, which is 2 squared, minus 1/2, 2 over 4, and this is 2 to the 4th, and the 0 again won't affect anything, so we don't have to plug it in. And if you do this math here, you should get 8. So all of this will reduce to 8 d theta. And the antiderivative of 8 d theta is just 8 theta from 0 to 2 pi, which is equal to 8 times the quantity 2 pi minus 0, which is 16 pi. Okay, and we didn't need to draw a picture on that one. You could plot that if you want to in 3 dimensions, like go to GeoGebra 3D graphing and plot the z and kind of get a sense of what it looks like. But we don't necessarily have to if we just convert to polar and think about it. So that would be problem 6. Problem 7, so use polar coordinates again, and it says inside the sphere, so let's see what we got here. Now, inside the sphere, x squared plus y squared plus z squared is 25. Now I'm going to immediately isolate z from that. So z squared would be 25 minus x squared minus y squared. Or z itself is equal to the square root of 25 minus, I'm going to factor out a minus here, x squared plus y squared. Well, that means z is really the square root of 25 minus r squared. So that's part of it. And outside the cylinder, x squared plus y squared equals 4. So x squared plus y squared equals 4. So that means r squared equals 4, or r equals 2. Now it says we want to be outside of, so this one, this represents a sphere, and this one represents a cylinder. And I'm not even gonna, boy, I don't think I want to try to draw that in 3 dimensions. I'm sure I'll butcher it. So we want to be outside the cylinder but inside the sphere. And so our r value has to be bigger or equal to 2. That would put us on the cylinder or outside of it. The sphere, notice from this that r has to be smaller than or equal to 5. Why? Because if r is bigger than 5, we're going to get a negative square root here. So the biggest r can be for the sphere is 5. So we're going to sandwich the radius between 2 and 5. Okay, then we're going to sandwich theta between 0 and 2 pi like most problems have it. And that's the hard part. So once we get the limits of integration and we have the equation for z, we just plug it into our formula. 0 to 2 pi, 2 to 5 of the square root of 25 minus r squared. And then it's r dr d theta, which is dA. Okay, to do this problem, we are going to want to use substitution. So we're going to let u equal 25 minus r squared. And therefore the derivative of u is negative 2r dr. And rearranging for dr, we would get dr is du over minus 2r. And I am going to change the limits of integration here. So if we plug in the lower limit of 2 into this u function, we'll get 25 minus 2 squared, which is 25 minus 4, which is 21. And u of 5 is going to be 25 minus 5 squared, which is 25 minus 25, which is 0. Okay, so we go and we change these limits, 0 to 2 pi, 21 to 0. Be careful here. It actually goes from a bigger number to a smaller number, which can happen. It's fine. And now we have the square root of not 25 minus r squared, it's the square root of u, and then it's r, and then dr is replaced with du over negative 2r, then d theta. And as I've said many times, if we've done this correctly, these r's should cancel, and they do. So this minus 1/2 I'm going to pull all the way out. It's minus 1/2, 0 to 2 pi of 21 to 0 of u to the 1/2 power du d theta. And this is going to equal minus 1/2 0 to 2 pi. Antiderivative u to the 1/2 would be u to the 3/2 over 3/2. And that's from 21 to 0 d theta. Dividing by 3/2 is the same as multiplying by 2/3, so that's going to come all the way out of the integral and be minus 1/2 times 2/3, antiderivative 0 to 2 pi, and it's going to be 0 to the 3/2 power minus 21 to the 3/2 power d theta. And I'm looking, it's not great. 21 to the 3/2 power is, let's see. So 21 to the 3/2 power, you can write it as 21 times the square root of 21, which I guess I will. So what we're going to get is this 0 goes away. This minus will cancel with that minus. This 2 will cancel with this 2, so we get 1 over 3 times 21 root 21, and that's all just a constant compared to 0 to 2 pi d theta. And so we're going to get 1/3 of 21 is 7, and we're going to get the antiderivative of d theta is theta, and that's going to go from 0 to 2 pi. So we're going to get 7 root 21 times the quantity 2 pi minus 0, and that is 14 pi root 21. I got some error here. Let me see what happened. The answer is 28 pi root 21, so I'm off by a factor of 2. Okay, I realized my error, and unfortunately I have to draw this thing to explain it. Okay, so we have a sphere of radius 5, and we have a cylinder of radius 2. And we want this thing, so this cylinder is going to take up this space here, and we want the volume, we want this volume outside of this red cylinder but still inside the sphere. Now the problem is what we just calculated, the way we set it up, was just the top part, the top half of this sphere and cylinder combo. So we need to double everything to add in this bottom chunk as well. So all I have to do is add a 2 in front of all these integrals. So we have to double this volume to get the full sphere and cylinder combo. And that's going to percolate all the way down to here, here, and here. So we're actually going to need to double that 14 and make it a 28. Okay, so we tend to set these up so that they're above the XY plane, but that's only half the story in this case. So they did not tell us we're only going with half of we're only going above the XY plane. They want the whole thing. So they want the sphere and the cylinder above it and below the XY plane, hence the doubling of these values. Okay, that'll be problem 7. Okay, problem 8. They have an iterated integral, and they want us to go from 0 to a and negative square root of a squared minus y squared. And the function, is kind of hard the way they have it written there. 0, the function we're evaluating is 2x squared y dx dy. Okay, now we want to put this in polar coordinates. So we're going to say we have 2x squared y is going to equal 2. X is really r cosine theta, but we're squaring it. And y is really r sine theta. So we're going to get, this is 2 r squared cosine squared theta times another r sine theta. So what we're integrating is actually 2r cubed cosine squared theta sine theta. So that is the function with respect to r and theta that we're going to actually integrate. Now the limits of integration, notice that this is x, so x is equal to negative square root of a squared minus y squared. And to solve that, we're going to square both sides. We'll lose the minus sign, we'll lose the square root symbol. A squared minus y squared. But I can add y squared to both sides and get a squared. Therefore, x squared plus y squared, which is r squared, equals a squared, or r is equal to a. Okay, now for theta, if our dy goes from 0 to a, okay, so let's write this. On the y-axis, they're saying y goes from 0 to some a value. Positive a must be along the positive y-axis. In terms of theta, that means I'm starting at the x-axis and I'm going to the y-axis. So that is theta, which would be going from 0 theta to pi over 2 theta at the y-axis. So we're going to write our limits as 0 to pi over 2 for theta. Radius goes from a to 0, so we keep this 0 here. And we prove that the square root of a squared minus y squared is a. Then we have all of this stuff. So we have 2r cubed cosine squared theta sine theta, and then dx dy is going to change to r dr d theta. Okay, so we're going to get the first variable we're considering is r, and notice when I add r dr d theta that this r cubed becomes r to the 4th. So we're going to get, let me pull this 2 all the way out, 0 pi over 2, a to 0 of r to the 4th, and then we have cosine squared theta, sine theta, dr d theta. This would be 2, 0 to pi over 2, of r to the 5th over 5, and then that's going to go from a to 0 of cosine squared theta, sine theta, d theta. Now this upper limit 0 is going to plug in here and be 0 to the 5th and just kill everything off. I better actually show this one. This would be 2. Let me write it as 2/5. Pull this 1 over 5 out front. This will be 0 to pi over 2. And this is going to be upper limit, which is 0. So it's 0 to the 5th minus lower limit, a to the 5th. Then that's times cosine squared theta, sine theta, d theta. But that's going to be minus a to the 5th. And that's just a constant, so I'm going to pull that out. And we're going to write this as minus 2a to the 5th over 5 times the antiderivative of 0 to pi over 2 of cosine squared theta sine theta. Now to do this antiderivative, we're going to let u equal cosine theta. Therefore, the derivative of u is equal to minus sine theta, d theta. Therefore, d theta is du divided by minus sine theta. And when we plug this in, I guess I'll change the limits of integration. So u of 0 would be cosine of 0, which is 1, and u of pi over 2 is cosine of pi over 2, which is 0. So we're going to get minus 2a to the 5th over 5 times the antiderivative of 1 to 0 of u squared times sine theta d theta, but d theta is du over minus sine theta. And once again, if I've done this correctly, anything with theta should go away. Now I do have a minus that sticks around. Well, this minus will cancel with this minus out front. So this is going to be 2a5 over 5 antiderivative 1 to 0 of u squared du, which is 2a5 over 5. Antiderivative of u squared is u3 over 3 from 1 to 0. So we're going to get this equals 2a to the 5th over 5 times 0 cubed over 3 minus 1 cubed over 3, which is just 1. 0 minus 1, which is 1, times 2a to the 5th. The 3 will stick around also, so we get 1/3. So it's going to be 2a to the 5th over 3 times 5, which is 15. Okay, so that will complete problem 8. Problem 9, we have theta goes, or x goes from 0 to 2, y goes from 0 to the square root of 2x minus x squared, and the function is 4 root x squared plus y squared. So let's start to rewrite this stuff in terms of polar coordinates. So we're going to have, let me write the original problem, 0 to 2, 0 to square root 2x minus x squared of the quantity 4 root x squared plus y squared dy dx. So let's start with the limit. This limit would be 2, no, let's not do it that way. So what we're going to write is that upper limit is a y term. So we're going to write y is equal to the square root of 2x minus x squared. And we're going to square both sides. And we're going to add x squared to both sides. And we're going to replace this with r squared. And we're going to replace x with r cosine theta. So recall, x is r cosine theta, y is r sine theta, so I can make those substitutions. And then we can divide both sides by r and get r is 2 cosine theta. So if I change this y to an r term, it's going to go from 0 to 2 cosine theta. Okay, so let's write that over here. 0 is going to be the lower value for r, and the upper value for r will be 2 cosine theta. Now the x term goes from 0 to 2, so we're going to have, actually to get the theta term, it helps to draw this picture. So let's go back to right here. If you subtract 2x from that, you're going to get x squared minus 2x plus y squared equals 0. And we're going to have we're going to complete the square and call this x minus 1 squared plus y squared equals 0. But by completing this square, I pick up a third term of plus 1. So if I pick up an extra plus 1 on this side, I have to add a plus 1 to that side. So this is x minus 1 squared plus y squared equals 1. And if you plot that, I guess I'll do it down here. That is a circle centered at 1, 0. So it's 0 in the y, 1 in the x. This is the center of a circle of radius 1. So we would have 2, 0, 1. This thing's going to look like this. And it says x goes from 0 to 2. So we got 0 to 2, 0 to 2. And y is going to be, and I should mention, we only get the top half of this circle because there's no plus or minus on that y. So if there was a plus or minus here, we would also get the bottom half of this circle, but there's not, so we're only going to have the upper part of this circle. And so to see theta, it's going to go from the x-axis only to here. That's all you need to capture this entire shape. So theta is actually going to be bound by, we saw this before, 0 to pi over 2. Okay, and with that information now, we can set up this antiderivative. It's going to go from 0 to pi over 2. It's going to go from 0 to 2 cosine theta. And then we should have written this as an r, so this would be 4 square root of r squared, which is just 4r. So we get our function is 4r, but then we add the r dr theta. So this is going to be the antiderivative 0 to pi over 2. I'm going to pull that 4 out front. 0 to 2 cosine theta of r squared dr d theta. And when we take the antiderivative of that, we're going to get 4 0 pi over 2. The antiderivative of r squared is r cubed over 3. And we're evaluating that from 0 to 2 cosine theta. And then we have d theta. Well, this is going to be 4/3 antiderivative of 0 to pi over 2. When we plug well, let me just show it. We're going to get 2 cosine theta cubed. Actually, I pulled out the divide by 3, so I don't need to write this as a fraction. Minus 0 cubed. And so we're going to get, this is going to be 4/3 antiderivative of 0 to pi over 2 of 2 cubed, which is 8, cosine cubed of theta, d theta, and the 0 will go away. Okay, then we are going to have, let's pull out the 8 and call this 32 over 3, antiderivative of 0 to pi over 2, and I'm going to do a slight trick here. I'm going to write this as cosine squared theta times cosine theta d theta. So I'm going to break up cosine cubed into a squared cosine times a 1 cosine, which is cosine cubed. Then I'm going to use an old trig property that says this: cosine squared theta plus sine squared theta equals 1. Or cosine squared theta equals 1 minus sine squared theta. So watch closely. We're going to write this as 1 minus sine squared theta times cosine theta d theta. So I just move this sine squared over here and solve for cosine squared from that old trig property, Pythagorean property of trig, and we're going to get this. Okay, and because of that, now we can do a u substitution. So we're going to let me see what I did here. Yeah, I believe we can do the whole thing. So let's let u equal 1 minus sine squared theta. Therefore, derivative of u would be minus, no. That's not what we want. We're just going to let u equal sine theta. Therefore, du equals cosine theta and d theta. And therefore, d theta is equal to du over cosine theta. And so what we're going to get is 32 over 3, 0 to pi over 2. This would be 1 minus u squared times cosine theta d theta, but that's du over cosine theta. And if we've done this correctly, cosine theta cancels with cosine theta, and we get this to be 32 over 3, 0 to pi over 2, and this is going to be 1 minus u squared du. And let's change our limits of integration. So u of 0 is sine of 0, which is 0. So that limit does not change, it's 0. U of pi over 2 would be sine of pi over 2, which is 1. So let's change that upper limit to 1, and then I don't have to go back to sine. I don't have to back substitute the u. So we're going to get 1. Now the antiderivative of 1 is just u from 0 to 1, and the antiderivative of negative u squared is u cubed over 3 from 0 to 1. And so we're going to get, from the first term, 32 thirds. From the second term, we're going to get minus 1/3. And the zeros won't change anything. And so we're going to get okay, but you'll notice I forgot to distribute this 32 over 3 to both terms. So this is 32 over 3 here. And so we get 32 over 3 times 1, which is right. Then we get 32 over 3 times 1 over 3. So this is minus 32 over 3, which is 32 over 9. Oof, running out of space here. So we're going to get 32 over 3 minus 32 over 9, which is 96 over 9 minus 32 over 9. I don't usually show this level of algebra detail, but this problem got a little messy because I forgot this term down here. And that's going to be 64 over 9 when you subtract those two numerators. And that would be the correct answer for problem 9. Okay, almost there. Problem 10. Find the average value of the function f of xy equals 5 over x squared plus y squared on the annular region. Okay, so let's draw this. So we have f of xy equals 5 over the square root of x squared plus y squared, which we're going to immediately change to 5 over the square root of r squared, which is 5 over r. Okay, so far so good. Now it says a squared sandwiches x squared plus y squared sandwiched below b squared. And then it says a is positive, bigger than 0, but smaller than b. Well, this is really r squared. And if I square root everything, this is saying the radius is sandwiched between a and b. So if we draw that, that is two circles, A and B, that go all the way around. So that's the radius A circle, this is the radius B circle, and the region we're looking at is right there. So we can immediately write that theta goes between 0 and 2 pi, the radius goes from a to b, and the function we're solving is 5 over r. And then we add in our r dr d theta, and the r's cancel, and the 5 can just be pulled out. Wait, careful. This is the equation if we're just trying to find the volume using double integrals. But this wants the average value of the function. So the average value of a function is equal to 1 over the area of the region, then times the double integral of the function r theta r dr d theta. So we have to add in front of this double integral 1 over the area of this region R. Well, the area of that region R is the difference in the areas of those two circles. So the area of that region would be pi r squared for both. So it would be the bigger circle, which would be pi b squared, which is the radius for the circle at B, minus the area of the smaller circle, which is A, pi a squared. And we can factor out a pi and call this pi b squared minus a squared. So that's the area of that, what we would call a washer. And 1 over that has to go in front of this integral. So that area goes in front of this double integral. And we notice the r's will cancel, and the 5 will come out front, so we're going to get 5 over pi b squared minus a squared. That's the area from 0 to 2 pi, from a to b, of just dr d theta. So this is going to give us 5 over pi b squared minus a squared. The antiderivative of dr is just r, so it's going to be 0 to 2 pi r, and that varies from a to b. And then we have our d theta. This is going to equal 5 over pi b squared minus a squared. The r evaluated from b to a would just be b minus a, and that's just a constant, so we can pull it out. Then we have the antiderivative from 0 to 2 pi of just d theta. Well, that's going to give us 5 b minus a over pi b squared minus a squared. The antiderivative of d theta is theta from 0 to 2 pi, so we're just going to get 2 pi minus 0. And that will just give us 2 pi into the 5, so it's going to be 10 pi b minus a over pi b squared minus a squared. And that would be correct and complete for problem 10, and that would finish off chapter 15, section 3.